let's make this into a triangle and measure out the triangle. So I need one more segment. There we go. And I'm going to measure that triangle. So I'm going to go click on A, and then B, and then C. And this tells you a lot of things. So it tells you all of the lengths, and it tells you all of the angles, and it tells you what the sum is of the angles if you add all three of those together, and it tells you the area. It would be a fun excursion sometime to talk about hyperbolic area and why that's given as a number of degrees. But it turns out that area and angle sum are related in a way that's really, really nice for this model of the hyperbolic plane. All right, so let's play around with this triangle for a minute. And so I'm just going to observe some things about this triangle that I can observe without actually paying attention to any of the measurements. I'm going to ask you on your homework explorations to pay attention to some of these measurements. But I'm just going to drag around my triangle a little bit, and I'm going to try making a triangle that looks really small. So I'm going to put A and B really close together, and I'm going to bring C over really close to them. And when I have those points really close together, it looks like a Euclidean flat straight triangle. So that's a thing to notice. Triangles look more normal on a hyperbolic plane if they're really small. That's also true of triangles on a sphere. All right, you are living on a sphere right now, and if you got down on the dirt outside and you drew a triangle and used string to make sure your lines were straight, it would look like a normal flat piece of paper triangle, because your triangle is very small compared to the size of the Earth. But when we make one of those wedge triangles where you start at the North Pole and you go down to the equator and then across, all right, so you're taking a big piece of the sphere, then that big piece of the sphere looks really different. It doesn't look like a normal flat triangle. And the same thing is going to be true here in hyperbolic space in a way that is somehow opposite to what happens on a sphere. So now I'm going to try and make a really big triangle. So I'm going to try and make A, B, and C as far apart from each other as I reasonably can. And so there we go. That looks pretty good. And you notice that's really stretched out. A kind of surprising thing about triangles in hyperbolic space is that if you're looking at how much area they enclose, it looks like there's kind of a biggest amount of area that they can enclose. If I try and take A and B and C and move them out as close to the edge of the disk as I can, oops, then, you know, I'm not going to be able to get the triangle to be bigger than that. There isn't a biggest triangle on a flat plane. Your biggest triangle is only bounded by how big your piece of paper is. And if you make a bigger piece of paper, you can make a bigger triangle. But on the hyperbolic plane, somehow, no matter how big your hyperbolic piece of paper is, you can only get so big. And you may have noticed that when I was trying to make a triangle with my crocheted triangle, or on the neck of a bottle triangle, you know, I have to make that triangle pretty small in order to get those hyperbolic line segments to intersect at 3 points. You get it too far away, and all of a sudden they don't intersect. Let's take a look at that on the hyperbolic plane again. This time I'm going to use infinite lines. So when I do this, it's going to give me an infinite line, and there's another infinite line, and there's another infinite line, and I'm going to move these around, and I'm going to try and make a triangle out of them. And you notice that right now I have 3 lines. All of them are non-intersecting, so they're all parallel, if my definition of parallel is that they don't intersect. What a weird idea for parallel. And they don't intersect at all, but I'm going to make a triangle, so I'm going to move this one over so it intersects, and then I'm going to move this one over so it intersects with this line on the bottom right, and then I need to move it over so that it intersects with the line at the top. There we go. And you notice I had to move things closer together. I had to make them pretty close to each other to even get intersection points to make a triangle at all. So that's one of the weird, interesting things that happens with hyperbolic geometry. All right, and so your job with hyperbolic geometry right now is not to, go out and learn how to integrate to find hyperbolic lengths, though there's lots of web pages that'll tell you how to do that. Your job is to kind of get a mental image, maybe with this Poincare disk model. That's going to be one of our favorites, one that we're going to come back to again, and get kind of a feeling for what do hyperbolic lines look like? What do hyperbolic triangles and angles look like? How is the hyperbolic plane similar to and different from the main Euclidean geometry that we're studying?